Hello everyone, I welcome you all to this session of phase diagrams and phase transformations in ceramic systems. This is lecture 3.3. In the previous lecture, we discussed about invariant reactions like peritectic and eutectic reactions where the miscibility gap is there in the solid phase and it evolves and becomes the eutectic and eutectic as well as the peritectic type of reactions. In addition to that, we also discussed about various different kinds of compounds. They are congruently melting compounds, incongruently melting compounds, and also compounds which undergo dissociation, sometimes at low temperature, sometimes at higher temperature, sometimes they have both higher and lower temperature dissociation characteristics. So in this lecture, this is lecture 3.3, in this lecture we will continue the discussion on miscibility gaps in the liquid phase. So as we discussed, what is the origin of miscibility gap? The origin of miscibility gap is the repulsion between the components. The repulsion between the components, if the repulsion exists in the solid phase, if they repel in the solid phase over a range, over a composition range, over a temperature range, then you see a miscibility gap there. That's a synclinal type of behavior, synclinal type of diagram. Now, in this case, we have another condition, that is, if they repel in the liquid phase, however, there is no interaction in the solid phase. This looks a little counterintuitive, but it is possible in few systems. Okay, we'll discuss about those systems. So consider that if A and B undergo repulsion in the liquid phase, they do not want to stay together. Okay, there exists a miscibility gap, or they are immiscible because of the repulsion between A and B in the liquid phase. Now, and if they do not interact in the solid phase, then the interaction parameter goes this way. The interaction parameter, that is omega, in the liquid phase is greater than 0. That we ascribed as repulsion behavior, right? And omega s is nearly equal to 0. So what is the deviation here? The deviation was, if both the interaction parameters are nearly 0, then that gives an ideal kind of behavior. It is an ideal isomorphous behavior. In this case, the interaction parameter in the liquid is being positive. In the solid, there is no interaction, it is nearly equal to 0. This is the deviation that we are going to discuss in this lecture. Okay, now this gives you the behavior which is drawn in this way, where temperature versus composition of B on the x-axis, and you see there is a miscibility gap. The miscibility gap in-houses two liquids, liquid 1 and liquid 2, and outside that you have only pure liquid. This is second type of binary phase diagram in our classification, that is purely synclinal type of phase diagram. And this diagram, this dome is shaped in a way that above this temperature there exists a complete miscibility. Understand? So this is called upper consolute temperature. Okay, now at this stage it is difficult to understand how do you distinguish two liquids in expense of liquid. Understand? It is very difficult to understand. Now you just take this as an information at this stage, that within this particular range of compositions and within this particular range of temperature, the liquid destabilizes, the homogeneous liquid destabilizes and becomes two liquids. And what is the distinction between these two? The distinction between these two need to be defined based on the fundamental definition of phase. What is the fundamental definition of phase? Physically distinct, chemically homogeneous and mechanically separable. Now you see, are these physically distinct? Yes, they are physically distinct. Why? Because they have different compositions. Since they have different compositions, there exists a boundary. Don't think like a oil water system. It's not an oil water system. Everything is oil. Only the compositional gradient is there. Okay. Now, since they are their chemical composition is different, though they are chemically homogeneous, both constitutes A and B only. Okay, but the compositional variation, due to the compositional variation, there exists a physical boundary. So that's how they can be physically distinguished. And since they are physically distinguishable, they have a boundary, they can be mechanically separable as well. Okay, so that's the reason L1 and L2 are now ascribed as different phases. One best example I would like to give here is a ceramic system, that is FeO and SiO2. Okay, here you see there is a miscibility gap here. Though the complete dome shape is not can be seen from this diagram, because this is only up to 1800 degrees Celsius, but if you see that if you go at a little higher temperature, there exists a upper consolute temperature and there exists a dome here, and within which you have two liquids, but outside that you have a completely single liquid. Okay, let's analyze this particular example. Now if you see, if you consider this example, we are deviating from the ideal isomorphous. Let's see how much deviation we have compared to the isomorphous criteria. So if it is a metallic system, the criteria was Hume-Rothery rules. If it is a ceramic system, we have modified rules that in-houses the oxidation states, polarization effects, and also defect chemistry. Okay. Now if you see, FeO is simple ionic structure. Say Fe2 plus is there, O2 minus is there. It acts as a network breaker. I'll tell you what is a network breaker. Okay. Now if you see SiO2, it's a strong covalent network is there, and the network of SiO4 polyhedra. Understand? And this is the understand like this is a polymeric chain. The moment you add FeO in it, it's an ionic molecule kind of stuff, so it breaks that network. Understand? So the original structure, that is a continuous polymeric network of SiO4 tetrahedra, is now broken because of the presence of FeO. So structurally they are different. So what was the first thumb rule? The thumb rule was both should show nearly same crystal structure. They should show same crystal structure. Here they are structurally too much distinct. They are completely different structurally. So that's the reason we are deviating from the ideal isomorphous one. And the second one is the SiO is a strong covalent directional bond. However, if you see, FeO is an ionic system, so there is a bonding mismatch as well, and there is a coordination mismatch also. I want to say that this is not an isomorphous. Iso is same, morphous is type. They are same type, but these are not same type because they have different bonding characteristics. They have different coordination. They have different coordination number. See, for Si it is tetrahedra, so 4-fold is there. However, Fe you have octahedral. It's an irregular octahedras. Understand? And they act as the network breakers. Understand? So that is the reason why there is a coordination mismatch, I can say. In addition to that, because of these all deviations, the liquid separates into two different phases. The first phase is the liquid with FeO rich, which has more network breakers. There is no continuous network as such. But the other liquid is SiO2 rich, which has a network structure. So first one is the ionic melt and second one is the polymeric network kind of structure. So structurally they are distinct. So that's how there exists a boundary. That's how they are distinct. Understand? Then immediately the question comes, yes, in liquid it happens, how about in solid then? The solid also they should show the mismatch. Yes, it is true. In certain, it depends on system to system however, but in this system, in the solid, the minimization of the Gibbs free energy takes place by forming a compound. So, although you have the tendency of mismatch, phase separation in the solid, in this case, the further minimization of the Gibbs free energy takes place by forming a compound. Understand? So that's the reason we generally don't suddenly see or recognize the miscibility gap in the solid when it comes to FeO and SiO2 structure. So ultimately, the minimization of the Gibbs free energy is important. Because in the phase diagram we represent those phases which have minimum Gibbs free energy. And along the phase boundaries, there is a coexistence of phases where the Gibbs free energy of the phases is same. Okay. Now, that's the reason we see liquid miscibility in these type of structures, in these type of binary systems. Okay. Now, understand that the interaction parameter in the liquid, it is important to be positive in order to show liquid miscibility. But is there any effect on the magnitude of that? If it is slightly positive, suppose say, is near to 0, slightly positive, or it is being positive, understand, relatively, I am talking about relative, relative quantities, okay. So the magnitude of the interaction parameter in the liquid also plays an important role. Here you see, I am just introducing the miscibility gap because of the interaction parameter in the liquid being positive, okay. Now, instead of forming one liquid within this composition range over this temperature range, I have two liquids. It means whenever I solidify it, the solidification sequence of both the liquid is different, because L1 is A rich liquid and L2 is B rich liquid. Similar to our previous example, one liquid was FeO rich and another that is like ionic melt, and another was the SiO2 rich. Okay, so in this case, L1 is A rich and L2 is B rich. Okay, now these two liquids will solidify separately. Let's do let's go through that. So there are two options. One is both the liquids can solidify together. That's one option. And the second option is these both the liquids, they solidify differently, and one liquid solidifies first and another liquid solidifies later. Understand? So these are the only two possibilities we have. The first one is, out of these two liquids, let's say that one of the liquids solidify first. For that, I am just adding the part of isomorphous diagram, because it all evolved from the isomorphous. We are deviating from the isomorphous. So I should have some traces of isomorphism here. So these two-phase regions, the lenticular type of two-phase regions, are the contributions from the isomorphous diagram. Okay, and this alpha is the single phase. Understand? Now, let's go a little further. If I complete the diagram, it looks something like this, where you have single liquid which dissociates into L1 plus L2. Now, if I take an alloy and start cooling it, then what happens with this composition? This composition is L1 composition. Why? Because it is near to the A, pure A. This L1 is a pure A-rich liquid. Now, L1 of this composition undergoes the solidification and forms the L2 of this composition. This analysis can be done through tie line. Okay, so one end of the tie line is L2, another end is L1, because one is single phase, another one is here also single phase, and the tie line passes through a two-phase region. That's the characteristic of tie line. So L1 of this composition transform into L2 of this composition. This happens at this particular temperature, this particular isotherm. It means this point is an invariant point. Now let's do that exercise. L1 gives L2 plus alpha. Out of two liquids, one of the liquid will undergo solidification or transformation. One of the liquid, it means mono. Transformation is tectose, monotectic. So this type of reactions are called monotectic reactions. Out of two liquids, one of the liquid undergo transformation into another liquid and a solid. So if I apply Gibbs phase rule at this point, you have three phase equilibria is there at this point. What is that? What are the three phases? L1, L2 and alpha. So that's how you get what? F is equal to 0. It's a monotectic invariant reaction. And another logic here I would like to say that since the phase separation takes place in the liquid phase and they undergo solidification, so we generally do not see the terminal solid solutions in the monoclinic structure, monotectic reactions, monotectic phase diagrams. Why? Since they undergo solidification, the expected solid solubility also at lower temperature is restricted. So that is the reason here I have shown a most generalized type of phase diagram. But if you see most monotectic phase diagrams, they do not have the terminal solid solutions. Okay, now one of the liquid has undergone the transformation into another liquid and a solid, and this liquid also has to go undergo transformation, right? So that liquid, we need to find out an invariant reaction where one liquid gives two solids, because at low temperature also there is no solid solubility. So the only option I left with here is L2 gives alpha plus beta. That's a eutectic reaction, one more invariant reaction here. So that's why the monotectic reactions are always associated with a eutectic reaction, or a reaction which gives solid phase as an output. Understand? So three things. One is the liquid phase separation happens at a higher temperature due to interaction parameter being positive in the liquid state. In addition to that, at low temperature the phase separation persists. That's the reason we don't see the terminal solid solutions. However, I have shown you here for the most general case. But if you see in real systems, you do not see the terminal solid solutions. Okay. Now, if I still increase the magnitude of interaction parameter, then what happens? Then the important point here I would like to mention is the miscibility gap will increase. Increase in the sense the volume of that gap will increase. The area of the miscibility gap will increase here. Why? Because now the more composition is involved in the phase separation here, and the temperature range is also increased. Now L1 and L2 has formed. More L1 and L2 has formed, and both have to be solidified. So I need two invariant reactions. Those could be two eutectic, two peritectic, one eutectic, another peritectic, or whatever combination. But the output should be, we have to choose those invariant reactions for which the output becomes a solid. Okay. Now where is the invariant reaction here? Now in this case, since both L1 and L2 are more in fraction, understand? So both L1 and L2 undergo transformation together. Unlike monotectic, here they undergo transformation together. So here I have added two eutectics, and to show transformation, because I need to have some transformation here. Why? Because otherwise I will be stabilizing both the liquids at low temperature, which is not possible. Liquid is always stable at higher temperature. So how can I stabilize a solid from two liquids? I need to have a solid which is stable up to higher temperature. That is possible if I add a compound here, kind of a compound, or the region of composition, the variation composition of that compound is still exists, but I have to have a solid which is stable up to higher temperature. So that I have added here. So that's a delta. Now if I complete the phase diagram, it looks something like this. You have a miscibility gap in the liquid, and which is accompanied by two eutectics, and this compound which divides the entire phase diagram into two simple eutectics. Understand? So because a compound which is having some, or a solid, let's call it a solid instead of calling it as a compound, this solid now divides the entire phase diagram into multiple subdiagrams. Okay, now what is this point then? Here two liquids transform into a solid. It means at this point of this, at this composition and at this temperature, this point, there is a three-phase equilibrium. Understand? So if I draw it, if I calculate the degrees of freedom, I get 0. It means this point is an invariant point. I do not have freedom of changing either composition or temperature, otherwise I will be missing out this point. Now both the liquids undergo transformation together, synchronized transformation. So SYN is together and undergo tectose transformation. So these type of reactions are called syntectic type of reactions. So the liquid miscibilities or miscibility gap in the liquid gives rise to two invariant reactions. One is the monotectic reaction, second one is the syntectic reaction. However, the miscibility gap in the solid phase has gave birth to two invariant reactions. Those are eutectic reaction and a peritectic reaction. So if I keep everything in a flowchart way, what all we have discussed. So binary phase diagrams are classified into three main categories. One is the lenticular type, ideal isomorphous system. Synclinal type, you have miscibility gap both in solid as well as liquid, and the merger of both lenticular as well as synclinal, this will give rise to different invariant reactions. Okay, now what are the variations in the lenticular type of phase diagram? One is pseudo-eutectic, there exists a minima in the liquidus because of the interaction parameter. Here the interaction parameter in solid being more negative, so it forms intermediate compounds. This is maxima in the solidus. In addition to that, in compounds, intermediate compounds or line compounds, we have three different types again. One is congruency, congruently melting compounds, incongruently melting compounds, and dissociation. And in dissociation, we discussed the limit of stability. Some compounds they dissociate at lower temperature. Some compounds dissociate at a higher temperature. Some compounds show dissociation characteristic at both higher and lower temperature. They appear as a floating vertical line in the phase diagram. So that is the third category. In addition to that, in the synclinal type, we discussed miscibility gap in the solid phase as well as in the liquid phase, and those gave birth to eutectic and peritectic type of reactions. In the case of solid phase miscibility gap, in the case of liquid phase miscibility gap, monotectic and syntectic reactions, and these two are also extreme cases of the third type of phase diagram, that is lenticular or lenticular plus synclinal type of behavior. Okay, now so all this comes under the total classification of binary phase diagrams. Now, but if you see particularly invariant reactions, so what is an invariant reaction? It doesn't have variance, it doesn't have degrees of freedom. Now, the maximum phases that are possible for a binary system which is drawn at a constant pressure is 3, because F is equal to 0 and binary system is C is equal to 2, and since I am drawing at constant pressure, so it is 1, so maximum is 3. It means the invariant point is a point where 3 phases are stable in a binary phase diagram which is drawn at a constant pressure. Okay, now it is most important take home information here I have mentioned, it is in a binary system at a constant pressure has three phases coexisting in equilibrium at an invariant point. Okay, now if you see the reaction, we see only two formats of the reaction. One is phase 1 gives phase 2 plus phase 3. These are all called eutectic type of reactions. And the second one is phase 1 plus phase 2 gives phase 3. That's a peritectic type of reactions. Understand? So, what is an invariant point in a binary system at constant pressure? It is, the invariant point is a point where three phases are in equilibrium. Okay, and definitely constant pressure condition is always to be mentioned. Now, what is an invariant reaction? Now, how those three phases are distributed in the reaction format. One phase gives two phases. If one phase is a reactant and two phases are the products, that is eutectic type of reaction. The transformation takes in this way. One phase gives two phase and three phase, phase 3, and the peritectic type is phase 1 plus phase 2 gives phase 3. The reaction between two phases give rise to a third phase. Okay, so don't restrict yourself to only the eutectic, peritectic, monotectic and syntectic reactions. We need to understand the format of the reactions. The generalized format of the invariant reaction is this, these two in a binary system. Now, if I categorize them, I can have list of permutation and combinations. For example, the eutectic type of reaction is the first reaction you see. One liquid, liquid 1 gives alpha plus beta, two solids, where alpha and beta are solids, gamma is a solid, L1, L2, L3 are liquids. Understand? Now, what is this? L1 gives L2 plus L3. This generally happens at a absolute temperature, where both all three phases coexist, all three liquids coexist. Understand? So, all eutectic type of reactions, if you see, one phase give rise to two phases. Now, a peritectic type of reaction is two phases give, results in one phase. The reaction between two phases gives a third phase. Okay. Now, out of these reactions, I would like to, I would like to mention two important reactions. These two are the important reactions. What is the difference between this reaction and all other reactions here? Because all other reactions, out of three phases, one phase is, at least one phase is a liquid phase. Here also, out of three phases, one of the phase is being liquid phase. However, these two are the important reactions. These two are very important reactions. If you see, they involve only solid to solid transformation. And if I say only solid to solid transformation, generally it happens at a lower temperature. So in the next lecture, we are going to discuss about this and what is the effect of solid to solid transformation and what these reactions are called. Okay, thank you.